Okay, section 4.2 area. So we want to look at this idea of finding area of a given region. In 4.2 we simply look at the approximation. And so suppose we'll just draw some area like this. Suppose I want to find that area. Well, what I could do is I can approximate it simply by, say, putting it on a grid. Right. One way to approximate this area would be, suppose each of these squares here is 1 square unit, and so I could say, oh, there's one, there's one, there's one, there's one, there's one, there's one. Now, each of these, we'll have that go right up there. Each of these is a full square unit, and then here, in all these others, I have a little bit, a little or a lot less than 1, right? And so as I look at this, 1, 2, 3, 4, 8. So my area, now what I can tell from this is bigger than 8 square units, but it would be smaller than if I toss in all these others, because all of those are bigger than the area they're looking at. If I toss in all of those, what do I have? 1, 2, 3, 4, 5, 6. 6 by 4. So I know the area is between 8 and 24 units. Now, I can make that better by making smaller grids and counting up the same way, right? I can get smaller pieces, and so I'll have more whole ones inside there. So this number would go up, and then this top number, the way I'm doing it, may not go down much, but it could go down because, see, before I counted, if we look at this top right corner and kind of blow it up, we had something that did that, and I counted that whole area. Oops. I counted that whole area as 1, right? But if I break it up like this, now I don't have to count those, and so I'm still getting a bigger estimate, but it's only 1/4 of a unit, square unit, instead of a full one. So this, should get bigger on this end by using more and smaller squares. And this side should get smaller. And eventually, if I do enough of these two numbers will get really close to each other, and it sounds a lot like a limit, right? I could ask, well, what's the limit of this as that square size gets down to 0? Okay, so that's the basic idea with area. Now, because we're working with functions, actually we'll do it slightly differently. So suppose, I just have some function here, f of x, and here's the axis, and suppose I just ask the question, say, I don't know, there's 1, there's 3, what's that area in there? Well, actually on 3 sides I'm in really good shape because I've got this nice rectangular sort of thing going on, and I can find rectangles just fine. But now, the question is, well, what about the top here? Well, since it's a function, what I could do is I could say go to the maximum of that function on the interval. I could go to the minimum, maybe that's there, of that interval. And theoretically, if I know the function, I should be able to get these values, right? And so the area, again, well, it would be, let's see, the width is 3 minus 1, so that's 2. So the area is bigger than 2 times f at x min, the x value that gives me the min, and 2 times f of x max. Sorry, got kind of crowded there, pretty ugly. Let me rewrite that. 2f at x min is less than the area is less than 2 times f max. Okay, so same idea, right? So whatever f of x is on that, you know, so a little more concrete example, let's take something like x squared. So here's the function x squared, and there's 1, there's 3, so this is x squared, and so what I know is that is 1, and that is 9, and so I know the area is between 2 times 1 area and 2 times 9. Okay, so I got an answer that the area is between 2 and 18. But I could maybe do a little better than that by doing the same sort of thing. Okay, there's my 1, there's my 3. But now let's make a new rectangle. And so once again, I could take the minimum on each of these pieces. Right, so I know that's at 1, this is 2, so that's at 4, and this one is at 9. And so for my minimum, I now have this rectangle and that rectangle that are definitely smaller than the area when I add them together. And so in this case, the width is 1, the height is 1, so I get my 1 times 1 plus, and then here I get a width of 1 but a height of 4, so 1 times 4, and that's less than the area. And then similarly, if I use these rectangles that are definitely too big, and so I have again a 1 times 4 for this rectangle here, and then the rightmost large rectangle I get 1 times 9. But so now you see I've made the area between 5 and 13. So see, this number went up, that number went down, and they've gotten closer together, right? And now I could go every half and so forth. Okay, now I could also write down what it is I just did here in this case, right? I took the 1 times 1 plus 1 plus 1 times 4. You know, what was that? What's another way to do that? Well, remember, this is just 1 times 1 squared plus 1 times 2 squared. Okay, that looks like a summation where what I've done, now I can drop the 1 in this case. So this is the sum, I equals 1 to 2 of I squared. Now I could toss in that it was times 1, but not real useful there. Okay, and similarly for the upper part, now I've got to, be careful about what I do here. So this is less than the area. Now here's a case where maybe I can do a couple different things with my summation notation. Probably the easiest is to just start at 2 and go to 3. Right? So I started at 2 and then went to 3 with this I squared times 1. Right? That gives me 4. 4. And then putting the 3 in, I get 9. Okay, so I've described it there. Now, I could also describe this function. It's a combination of what numbers I'm putting in and what I'm doing, but I could describe this function slightly differently. But since the function is, x squared here, I'll just use that function and call it I squared, since I'm letting I go from 2 to 3, or I go from 1 to 2. Okay, so this is the basic idea of area that we're going to try to do. And so now let's try to do a little bit more with this, but we'll start a new video to do that.